Okay, right. So today we start by doing something really simple and look at k equals 1, 2, 3, 4 in turn, and see which graphs have a k flow for these low values, small values of k. Okay, so we can't have a 1 flow because flow values have to be non-zero, and they can't be both non-zero and bigger than -1 and less than 1 at the same time. So 2 is where we start. Which graphs have a 2 flow? Okay, what do we have to do? We have a graph, and there's lots of edges, and we have to assign 1s and -1s to the orientations of those edges. Okay, so say a 1 here, a -1 there. And so on. Can we satisfy the two axioms F1, -1 in one direction, 1 in the other direction, and F2, the sum at any vertex of all the flow going out of that vertex has to sum to 0. Equivalently, all the flow going into that vertex through incident edges. So can we satisfy that? When can we? What do we need to satisfy that for? Just for 1s and -1s? Well, we need an even number of edges, obviously, right? Otherwise, we have more 1s than -1s or more -1s than 1s, and they can never add up to 0. Okay, and the first little proposition is that if we have all degrees even, then this can actually be done. Whereas that's not entirely obvious how to do it. Right? If we start locally at a vertex and assign happily 1s and -1s like this, and then this propagates somehow through the graph through other vertices, right? So when we get to a next vertex here and we had -1 in this direction, then obviously we have to have 1 going into that vertex there. But these also might have influence on that vertex somehow. And so it's not quite so trivial to do that. Any idea of how it could be done? Yeah? Yes, that's right. So if we take an Euler trail, and if the graph is connected, then even degrees ensure that there is such a thing. This winds through the graph, going through every edge exactly once. So we can assign 1 to the edges in the direction of travel by this Euler trail. And then it goes in, out, so we get a 1 and another 1, so this 1 would cancel with that -1 at every vertex, every time we pass through that vertex, and that'd be done. Yeah, that'd be good. Okay, that's a sort of fairly big gun for such a trivial little statement. So let me prove it by using an even bigger gun. And that is, last time we proved that k flows exist if and only if zk flows exist. Right? So instead of a 2 flow, if we consider it a Z2 flow, Z2 has only 1 non-zero element. That's the 1 mod 2. Right? So we just write 1 on every edge in both directions because 1 equals -1 in Z2. So we just have 1s all over the place. And since the degrees are even, we get sums that are, in fact, 0 mod 2. So everything sort of clicks into place immediately. Okay, how about 3? Well, we have some sporadic results here. Not particularly deep, not particularly interesting. But it's a small collection, so I may as well give you that collection. So a cubic graph, big restriction, has a 3 flows, a 3 flow. I have German notes here as you do there, so has a 3 flow. If and only if it's not if and only if it's bipartite. Yes, if and only if. Right, so once more. We assume that the graph is cubic, and then the following two things are equivalent. It has a free flow, and it's bipartite. Okay, so let's prove that if it has a free flow, then it can't have any odd cycles, and therefore must be bipartite. So let's look at a cycle. And once more, instead of a free flow, let's assume that it has a Z3 flow. So if we have, say, 1 mod 3 flowing through this edge, that assumption does not entail any loss to generality, right? It can only be 1 or 2. If it's 2, then the other direction would be 1. Because 1 is minus 2 in Z3, right? So let's just assume, let's find an oriented edge that carries the flow 1. And that exists. So how about this edge? Well, if this had 1 as well, we'd have a problem. Then we'd have 1 into here, minus 1 into there. They would sum to 0 already. But then our graph is cubic, and we need to assign something to this edge, and the something can only be 0, which we're not allowed to use. Okay, so this cannot be 1. If it's not 1, it only has the option of being minus 1, or equivalently 2. Right? So we alternate between 1s and minus 1s. That means the cycle must be even. Right? So the graph doesn't have any, if it has a Z3 flow, it doesn't have any odd cycles. All the cycles are even, and so it's bipartite. And if the graph is bipartite, that's just as easy. Cubic, remember? So any idea of how to assign flow values to these edges? Well, we want them to sum to 0 here, if they're all oriented away, say. Right? So we use 1 or 2, it doesn't matter, 3 times. That's the only way to get a 3-term sum equal 0. Right? So let's use 1. And then we may as well do that on all the edges. Always 1 from left to right. And that means that here, where degrees are also 3, we have 3 incoming edges, all with a flow of 1. So we have an outflow of minus 1s or 2s, and they also sum to 0, and that's fine. So that was easy. There's a cute little corollary, and that is that cubic bipartite graphs, right, those that have a 3 flow, can't have a bridge. It's cute because it doesn't mention flows. Right? You can ask yourself, if your graph has a bridge, so this goes on somehow, can you close this up, remaining cubic? The answer is actually yes, you can. It takes a little bit of fiddling, but you can't, and at the same time be bipartite. Okay, so that's a little corollary, which is sort of nice because it's a true corollary in the sense that it doesn't involve the terms that we had in our little proposition. Okay, on to 4. 4 is a little more interesting. Can you think of any graphs not too small? No, we're not talking about 4 just yet. Sorry. So the next proposition, the next proposition, 643, is to investigate complete graphs. I mean, that's one of the first questions one would ask if you have a new invariant, like the flow number. Can I say what the values are for the graphs that we deal with every day, like complete graphs or cycles or paths or whatever, trees? Right, so how about a Kn? Does Kn have an n flow? Can you think of some n that are really big, that have a k flow for really small k? For example, k equals 2. Yes, you can. That's right. You can just make n odd. All right, then the degrees are even, then we have a 2 flow. So that's that. Kn for n odd has a 2 flow. Okay, so let's talk about n even. For n equals 4, let's start at 2. How about K2? Come on. No? Yes. K2 can't have any flow. It's a bridge. K2 is a bridge in its graph, right? So the edge is a bridge. The edge of a K2 is a bridge in it. We can't give it a non-zero value and then at the same time have values sum to 0 at the 2 vertices. So K2 can't have any K flow for any K, and then we set the flow number to infinity. Okay, so next one is 4, K4, and I don't have anything clever on K4. You just sit down and fiddle a bit, and then you find that the flow number of K4 is in fact 4. Right? It doesn't have a free flow, but it does have a 4 flow. So, right, so that leaves us with n that are even and at least 6. So that's proposition 643. Let's look at the case n equals 6. Well, we have a Kn, right? Let's write it in a slightly funny way. 3 vertices on the left, 3 vertices on the right. And our aim is to show that it has a 3 flow. Right? It can't have a 2 flow. Kn for n even can't have a 2 flow because the degrees are not even. Right? So the best we can do is prove that they all have 3 flows. So for all even n at least 6, Kn has a 3 flow. That's the proposition we're proving. Let's do it for n equals 6. And the thing to observe is that we have a 2 flow here, and a 2 flow there, right? Just one round the triangle, one round the triangle, or because the degrees are even if you want to invoke that proposition. So we have 2 flows there, and then in between them, what do we have? We have a cubic bipartite graph, yeah. So we have a three flow in the middle. Okay, and we just add them. We take the union of these two flows. On these edges, we assign ones and minus ones, depending on how we chose those two flows. And here, on the middle edges, we use the values of that three flow of the bipartite cubic graph. And then we're done. Okay, so n bigger than 6, and here we use induction. So let's split off two vertices and consider the rest. Now, by induction, the rest is a complete graph on an even number of vertices, at least 6 of them, because now n is even and bigger than 6. So we have a three flow here. Let's use it and extend it. Okay, how do we do that? Well, every vertex in this kn minus 2 sends edges to both those vertices. And now we can send let's use a Z3 flow on here. Okay? Now send a Z3 flow around each of these triangles. And sum them all up. So we get 1, 1, 1, or maybe 2, 2, 2. Doesn't matter which. They have Z2 flows, but we don't want them. Remember, for fixed k, we can sum ZK flows, and we have a Z3 flow here, so we want lots of Z3 flows on the triangles. And the only thing that can go wrong is that when we sum up all these little Z3 flows over the triangles, on the triangles, then this edge E, which lies in all the triangles, somehow, by bad luck, is assigned 0. What can we do? Can we tweak what we have a little bit? Yeah, of course we can. We just pick one of those triangle three flows, Z3 flows, and if it says, say, sends 1 round here, instead we send two round there. Equivalently, we replace it by its additive inverse, by minus that flow. Either way, we still have a sum of lots of 3 flows, but here the value is not going to be 0. Okay. So now we get back to k equals 4. And here's a lovely little result that says that 4 edge-connected graphs have 4 flows. So that's 6, 4, 4. Actually, I should use the light. Okay. So, here is a line from your favorite really bad maths book. Proof, colon. What do we know about 4 edge-connected graphs? Let's try to use that. This is not how maths works in practice, right? You're not given a toolbox with well-defined tools, and then you say, right, and next I'm going to do some new maths by using those tools. So you are usually driven either by a problem, and the problem here is the obvious one, wish graphs have a 4-flow, and you don't just guess that 4 edge connected is the right or a right condition. You arrive there somehow. Or else, if you're not problem-driven, then at least you're driven by some intuition of extending the body of theory that you have in some reasonable, interesting way, but not just by saying, I use all the tools that I have and tinker with them a little bit and produce something new. That's bad maths. Okay, end of rant. So now, back to my bad proof. Correct, but bad proof. How can we use 4 edge connected? It's not so long ago. Yeah, we have the tree packing theorem, right? So 4 edge connected implies we have 2 edge disjoint spanning trees. A blue one and a red one, and a green one. So T1 or T2. Okay, so let's draw T1. Something like that, that's T1. And let's try and build up our Z4 flow. And one thing we can do is make all the chords happy. So if we have a chord here, like E, we can look at the fundamental cycle defined by E with respect to the spanning tree T1. And then we can send a flow, a Z4 flow of value 1 around this cycle, either way around. Okay, just 1 mod 4 along this edge E, this orientation, 1 here, 1 through there, 1 through there, 1 through there, once round. Okay, that gives us a circulation already on G, because all the vertices satisfy F2, and the inverse orientations we just assign the negative flow values to so as to satisfy F1. Okay, so we do that for every chord. Important, every chord, not just the chords that happen to be in T2, right? Remember, we have a packing, so we have 2 edges joined spanning trees, but they needn't eat up all the edges. So for all edges not in T1, those form chords, we use such a cycle. And then we sum those flows around those cycles over all these chords E. Let's call that F1. So F1 assigns non-zero values to all the edges not in T1, and maybe to some of the edges on T1 as well, but maybe not to all of them. So there may be some edges on T1 that have a 0 assigned to for both orientations by our circulation F1 on G. Okay, so let's make those happy as well. And since they're on T1, they're not going to be on T2. So here's T2. So these blue edges here are going to be chords of T2 somewhere, don't know where. And then we do the same there. So we send a flow around their fundamental cycles in T2 of value, well, not 1, but value 2. And 2 equals minus 2 in Z4, so I don't have to specify which orientation. Right. So then we consider F1 plus F2, and I claim that that is our desired Z4 flow on G. Now, we certainly have a circulation because we always kept axiom F2 at every vertex. Here we did by summing over these circulations defined by sending flow around certain cycles. Here we're doing the same again. So we certainly are a circulation, and the only thing to check is that we're non-zero everywhere. Well, F1 was non-zero except at these special edges to which we added 2. So on these special edges, we're not going to be 0 anymore. And we only added 2 once, right? Because each of them lies as a chord only in one fundamental cycle. And the same was true here. I didn't mention that earlier. But could it have happened that by adding all these flows round fundamental circuits of T2, we inadvertently changed non-zero values of edges under F1 to 0 values under F1 plus F2? No, it can't happen because 1 plus 2 is, oh, it's too hard. Minus 1 plus 2 is also too hard. But I'd tell you that much, it's not 0, not even in Z4, right? So edges that were happy under F1 are still happy under F1 plus F2, and those that were unhappy are made happy once, and when others are made happy in this same way, they remain happy as well. So that was that. That's pretty, eh? Questions about anything I've said so far? Right, they're all nice and easy. There's another nice and easy one. Okay, that's 645. A graph has a 4 flow, if and only if. That's something. It's the union of 2 even subgraphs. So a subgraph is even if all its vertex degrees are even, and union does not mean edge disjoint union. Right? So this graph here is a union of 2 even subgraphs, this cycle and that cycle. This edge lies in both. That's fine. Okay, so why is that true? Well, if the graph is a union of 2 even subgraphs, what can we do with an even subgraph? Well, it has a Z2 flow, right? And the other even subgraph also has a Z2 flow. okay? And now we want a four flow. Can we somehow combine them? Yes, of course we can. Yeah? Yes, that's a possibility, the way we just did it on the spanning trees. And formally, there's another way, which I could have used just earlier as well. We just do two components. So we take the product, Z2 by Z2, as our group. That happens to be the Klein 4 group, doesn't matter. So the elements are things like 0, 1 are pairs of elements of Z2. 0, 1, 1, 0, 0, 0, and 1, 1. Those are the four elements, right? And these zeros and ones are always zeros and ones in Z2. And addition is component-wise. So plus 1, 1 would be first component adds to 1, second component adds to 0. Right? Okay. Right, and that's it. So around each of these two even subgraphs, on each of them we have a Z2 flow, and so we combine those two to a Z2 times Z2 flow by sending each edge to the pair where the first component is its value under F1 and the second component is its value under F2. So for example, if we had one round here this way, well, this way doesn't matter because we're in Z2 and 1 equals minus 1. So we have a 1 here and we have a 1 here. And this edge now gets a 1, 1. And this edge, say if this is the second graph, gets a 0, 1. This edge here gets a 1, 0. Okay, all of them are non-zero in this group. Again, the other way around is just the same, right? If we have, on any graph, an H-flow for H this group, we just define those even subgraphs as the first one is those edges, consists of those edges and the entire vertex set, where the first component of our H-flow assigns a 1, that's a certain set of edges, and the second set of edges is those edges where the second component of our combined flow assigns a 1. Okay. And at every vertex, the flow values sum to 0. So in particular, the two components sum to 0. The 0 in this group is the element 0, 0. So both components have to sum to 0, so both components induce even degrees in the graphs I just defined. Questions? No. Then we have the second part of that proposition 645. So let me write this up here. This is 6, 4, 5, 1. And now 2, what does 2 say? Cubic graph again has a 4 flow if and only if it's 3 edge colorable. Now this is sort of funny. That colorings have anything to do with flows. That really is a bit funny. We'll get a lot more of that fun later today. Okay, so for the forward direction, assume that we have a foreflow and therefore also a Z by Z flow. Right, and now we need an edge coloring. And what do we use? We have a cubic graph. So we have a cubic graph with a Z2 by Z2 flow. And we color E with its value under this flow, with f of E arrow, where f is our given Z2 by Z2 flow. So is that well defined? Right, so we're coloring the unoriented graph. Yes, it is well defined because this equals f of E backwards because it equals minus f of E. So if you take an element of our group, this group, minus that is itself. Right, like same as in Z2, we just do it component-wise. So f of an oriented edge is the same as minus that value, which by axiom of f1 equals f of the other orientation. So those two f values are going to be the same, and therefore we can color the undirected edge E, unoriented edge E, with this well-defined color. Right, so back to our question here. Could we have a violation of that adjacent edges have to receive different colors? Well, if this and this have the same color, then that would be the same group element. And then the flow into here and the flow into there would sum to 0. Again, same reason, every element is its own negation. And then there would be nothing that the flow could assign to that edge, nothing non-zero. But we're assuming that it does assign something non-zero because we're starting from the assumption that we have a Z by Z, Z2 by Z2 flow. So these two adjacent edges do in fact receive different colors, and we have a proper coloring. And the other way around, if we have a 3-edge colorable cubic graph, how can we define a flow? Yes, shrug your shoulders, that's the right answer. We do it in exactly the same way. So we use the 3 non-zero elements of this group here as colors, as flow values. First as colors, then as flow values. So we have 3 coloring, but we can use our color pot, right? So it doesn't matter whether we color with red, blue, and green, or with 1, 2, and 3, or with the 3 non-zero elements of this group. And that's what we do. So these edges have those non-zero values of this group assigned to them, remember they're their own negatives in that group, so we assign that number to both orientations, and we're done. Right? We do have a flow because axiom F1 is clearly satisfied and axiom F2 is satisfied because these are different, the three different elements of this group. Here they are. Here are the three non-zero elements of that group. And if we sum them all up, then we get 0, right? So these sum to that, and adding that again gives us 0. Questions? Okay, and another little corollary is that cubic three-edged colorable graphs don't have bridges because they have these flows. Right, another cute corollary because it doesn't mention flows in the statement. Cubic, three-edged colorable, strange combination of assumptions, right? But well, there you go. Okay, they don't have a bridge. Right. So on to something a little more substantial. I think I'll wipe this. To start with, as they say, a clean slate. It's no longer a slate, but something like it. So the guiding question for the next section is, if we look at planar graphs, or plane graphs, graphs already embedded in the plane, do flows tell us something about flows in a plane graph? Tell us anything about the dual? Well, this question doesn't come out of the blue. It has a bit of a history, but let's just pursue it as it is. So we have a plane graph now, a graph drawn in the plane. Let's assume it's connected. Oh, and all the graphs now are going to be loopless too. So connected and loopless are assumptions that I'm going to make for everything today from now on. And suppose we have a flow on this plane graph. Can it tell us anything about the dual graph, the plane dual? Well, that's just the question. So in plane graphs, we have a dual, the primal graph G and G star, and we know that the bonds in G star are the cycles in G, right? This was an abstract duality. Otherwise, we would say there's a bijection between them. In abstract duality, we said we have one set of edges which we sort of lift off G and then sprinkle over the vertices of G star, and in such a way that what used to be the cycles, edge sets of cycles, become precisely the bonds of G star. And this phenomenon that such graphs G star can even exist for a reasonably large set of graphs G was the interesting fact, or one interesting fact. And this reasonably large set of graphs G, or class of graphs G, is the planar graphs. So for planar graphs, we can do that. They have such a dual, and they also have plane duals defined explicitly, as we did it earlier. Right, so we know something about flows and bonds. And this is really where the idea originates to even consider plane duality in the context of flows. Because flows tell us something about bonds, and bonds translate to cycles. So any flow on G star consider a flow on G star and call it little g. Right? I call it little g because the little f's are going to be things on G, on the edges of G later. So if we consider that, then we can also view it as a map from the edges of G to our favorite abelian group H. So, warning, I've already started cheating, and I'll cheat a little more. Right, so flows assign group values to edges of G star, but those are the same as the edges of G, so we get a map from the edges of G to this group. And we know that G is 0 on the bonds. So this map is 0 on the cycles. Okay, so that's interesting. We have a map on the edges of G that sums to 0 on all the cycles. So where did I cheat? I'm not a good liar. You see, I wiped something out here because I inadvertently wrote the correct thing. Of course, a flow is not a map on the edges. It's a map on the oriented edges. And if we have a map on the oriented edges of G star, that's what the flow little g is. A map on the orientations of the edges that are common to G star and G. But the orientations are defined, of these common edges, are defined separately and independently almost, well, we'll get to that, on G star and G, because you need vertices to do that. So when we have an edge, what are the orientations? Well, we said those are the pairs xy or yx of its ends. Right? So this had two orientations. We always have to name the edge itself at the start because we have multiple edges. So the two orientations were exy and eyx. Now, this is an oriented edge in G star, an orientation of an edge of G star, where the edge is also an edge of G, but this orientation doesn't make sense in G, because x and y are not vertices of G. So in order for any such statement, we need to refine the bipartition, the bijection between the edges of G star and the edges of G, which in abstract duality is just the identity map. This bijection to a bijection between the oriented edges of G star and G. So we need, or we want, bijections from the two orientations of an edge in G, say. I'm going from right to left now, to the two orientations of the same edge viewed as an edge of G star. Or in plain duality rather than abstract duality, E star is precisely the edge of G star that crossed little e in the drawing. Right? So we want bijections of these two sets to those two sets, one such bijection for every unoriented edge E. And then we can even begin to say that if we have a flow on G star, well, we have a map that assigns to every oriented edge some group value. Then we also have such a map on the oriented edges of G. And then we can ask, well, is it true that every flow on G star, which is 0 on the oriented bonds, right? A bond is a cut. Cut is witnessed by a bipartition of the vertex set and by an oriented cut, particular an oriented bond. I mean the set of all these edges all oriented the same way from one partition set to the other. To cycles with orientations. Okay? So if we can extend the bijection between unoriented bonds and unoriented edge sets of cycles to oriented ones, then what does an oriented bond in G star give us? Right, something like that. And we know that the sum over the G values of these oriented edges is going to be 0. What does that give us in G? Well, in G, we have these edges forming a cycle. Right, and we know that through this bijection here, the G value of some orientations of these cycles, so we have an oriented edge in G star, this one here, that corresponds via this bijection to an oriented edge on that cycle in G, for example, to this one. This is the first. The second could be perhaps this one. And the third could be that one, and the fourth could be this one, and so on. Every oriented edge is mapped to an of this bond is mapped to an oriented edge of this cycle, but the orientations on that cycle depend on how we chose these bijections. And they could be anything so far. So the question is, well, if we want something nice, some reasonable statement here, a translation of the fact that flows sum to zero over oriented bonds to the induced maps doing summing to zero on orientations of cycles. We want these orientations of the cycles to be not such chaotic orientations, but nice ones, either all edges like this or all edges like that. That would be really nice. And the question is, can we define this bijection in such a way that this works for all the bonds and all the cycles? Right? So it's easy to do it for one cycle. Right? One cycle has a certain set of edges that correspond to these edges in this bond. Right? So we could say, okay, left to right are certain orientations of these edges in that bond, and on those oriented edges of G star, we just choose these bijections on these little two sets in such a way that the images which are oriented edges of that cycle C all go around the same way. So that's easy to do for a given cycle, but G has many cycles. So, for example, here is another cycle. And we want one set of bijections between these two sets, one for every unoriented edge E of G, one such set of bijections that works for all the bonds and all the cycles. So this edge here receives, or its orientations are images of certain orientations of this corresponding bond that corresponds to this cycle, but this edge also lies in the cycle that corresponds to another bond, another bond corresponding to that cycle. And there we also have a left to right, or perhaps a right to left, but not something jumbled. And we would like that those orientations of that other bond also to correspond by the same choices of these bijections, including the one on this edge that has already been defined when we looked at this, to correspond to an oriented cycle, to a nice orientation of this cycle here, always round. Okay, so the question is, can that be done? And the answer is, yes, it can be done. Can I prove it? No. I can prove it, but not in this course, because that's sort of elementary topology. One has to prepare a lot more, do a more complicated setup, and then use something that is called the orientability of the plane as a surface. So the layman's version of orientability is that you can place a clock on your surface, and the clock tells you what clockwise and anti-clockwise means. And then you can move that clock around that surface, and you will never somehow end up with the clock sitting at the back of the surface over the same spot, suddenly declaring the inverse of what used to be oriented, what used to be clockwise as clockwise. So in some surfaces this can in fact happen. So if you take a Mobius strip, for example, which you know already, you put a clock on it, and you have it like this. So it's sort of flat like this, and as you go around, you cross a little, you twist, right? So that can be made, that can be closed, this Mobius strip, to make a nice closed surface. But never mind, put a clock on the top, go round, 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 and now you twist, and then the clock ends up underneath. So you cannot do that for all the surfaces. You can do it for something like half of them. Those are called the orientable surfaces. And the sphere, or equivalently, the Euclidean plane, is orientable. Okay, so that exists, and let me tell you how to define it in some not quite so rigorous way, just so that you have some idea. And this is, remember the dual graph we had in the plane. Now put a node or a vertex of the dual graph in every face. Every face became a vertex. Every face of G in the plane became a vertex of the dual graph. And then we added edges between adjacent faces, those that have a common edge of G, an edge of G on their two boundaries, by making a little bridge over this boundary and then traveling to the respective nodes. And those would be our nodes of G star. Right, and now you can say, okay, if we have an orientation of this edge E already, then we want to assign it an orientation of G E star. And which one do we take? Well, we just turn this according to our clock, anti-clockwise, for example. I mean, this is like a silly mathematician's joke. Pick an orientation of the plane, for example, anti-clockwise. Right? Normal people would say clockwise, but okay. So it's well defined. Sort of well defined now, right? If you believe the clock story, then it's well defined. You just put the clock on this intersection point there, and then the white edge is turned anti-clockwise to become the red edge, the orange edge. Okay, and if we do that everywhere, so here as well, for example, then this is a global way of defining these bipartitions just once for every edge. For every edge E, pick one orientation, turn it anti-clockwise to find exactly one of those two, and use it as its image. And then the other one, turn that anti-clockwise, look at the plane, and you will notice it becomes the other one. Right? Then that's a bijection, and it just so happens that this bijection works for our task, namely that of G star will now correspond to oriented cycles where the orientation of the cycle is really rounded one way or really rounded the other way. And that is the next lemma, the first lemma. To spell it out really formally, you look at a cycle in G, look at the set of its edges, then there is a corresponding bond of G star, namely in the plane, a bond that separates all the nodes inside this cycle C from those nodes outside the cycle C. And this bond now receives an orientation, our global bipartition, which we claim exists, ensures that if you pick one of these two sides, X or X bar, the inside or the outside of this bond in G star, and orient all the edges of G star from X to X bar, then these orientations correspond by this clock thing to orientations of C that are all the way around C one way or all the way around C the other way. So the next lemma relates flows to cycles. So we're assuming now, so this is now lemma 652. We're assuming that we have compatible maps from the oriented edges of E and E star to the same group. So E are the oriented edges of G, E star are the oriented edges of G star, and we're assuming that we have maps which we call F and G, which are compatible to our group, which commute with this bijection whose existence we have just shown or claimed. Right? So that's the setup for the next lemma. And the lemma says item 1, that G satisfies axiom F1 of flows if and only if F does. Right, and that's obvious, because F1 just means on every edge, if you add the value of an oriented edge to the value of its inverse edge, then the sum is 0. And since these are bijections here, if that is true in G, it must be true in E as well, because the pairs of inverses here correspond to the pairs of inverses there, and if their sum under G is 0 here, then through this compatibility, the sum of the corresponding oriented edges in G will also going to be is also going to be 0. So F1 is trivial. F2 is also easy. There's a little point where one has to be a little careful, but not much. So 2 says that G is a circulation, so the map little g satisfies F1 and F2 if the map F satisfies F1 and, well, we have to translate F2 now, right? F2 says that out of any vertex of the dual. If we sum over all the G values out of that vertex, then the sum is going to be 0. We're assuming this condition on G, that round every cycle, F sums to 0, and we want to prove F2 for G star. We have to prove that this G sums to 0 over all these cuts here. We write the cut as a disjoint union of bonds. We know that G sums to 0 over all these bonds because F sums to 0 over the corresponding cycles. So these all are zeros, and their sum is that, so F2 is satisfied. Okay. Right, and now comes our only theorem of the day. And that really is a nice theorem. It says, it relates the flow number of a graph with the chromatic number of its dual, or the other way around, when the graph is planar. And the way I've phrased it is that for a pair of dual plane graphs, G and G star, we have chromatic number of G equal to the flow number of its dual G star. Right. So remember that graphs only have duals if they're connected. And that's a reminder, so our graphs are connected. I don't have to assume it, because if we assume that we have a pair of dual graphs, they must be connected, because duals are connected, and each is a dual of the other. So they are connected, and also we're assuming they don't have loops. Right, and the induction is on the number of bridges in G. And this is a rare occasion where the induction step is easy and the induction start has a little more substance. So how does the induction step work? Well, if we have a bridge, so the induction start is when we have no bridges in G. Right? Now assume we have a bridge. This is our bridge E in G. Then contracting this bridge doesn't change any cycles. Okay? So the cycles, no cycle can travel along this bridge, and if we contract it, then we get the same cycles that were formerly there, and no new ones, and all the old ones are still there. So contracting an edge doesn't change the cycles. Deleting an edge doesn't change the cycles either, but that would disconnect the graph. We need connectedness. All right, so we contract the edge E for the induction step, and then what happens to the, what is E star? Well, E star is a loop, right? I said I didn't want any loops. Well, maybe at this point it's okay to have loops. Sorry, look it up in the text. So contracting E corresponds to deleting that loop in G star. Right, when we have contracted E, it's no longer there, and the loop E star then is no longer there, and therefore has been deleted. And so the induction hypothesis tells us that the chromatic number of G minus E, or sorry, of G contract E, is the same as the flow number of G star minus E star. And I've just told you that contracting the edge E doesn't change any cycles, and neither does it change the chromatic number. Right? So what's the chromatic number of this graph? It's the maximum of these three chromatic numbers. If there are any further edges, then if the graph isn't just a K2, which we assume, there are more edges going to be here. So the chromatic number of this graph is the maximum of the two chromatic numbers here. But that is still the chromatic number of the graph after contracting E. After contracting E, we have these two blobs identified in a vertex, and what's the chromatic number of that? Still the maximum of those two sides. So the chromatic number of E doesn't change when we of G doesn't change when we contract the edge E, and similarly the deleting the loop from G star doesn't change the flow number, because loops are disregarded in all the definitions that ever go into flows, into flows. We never, when we have F2, we ignore loops in the count. Loops have values on the flows, but we always ignore them whenever we sum over values of oriented edges. So that's also the same, and that's what we wanted. Right? So that's the induction step done. Let's now do the induction start. So we want to show that G has for every K, we want to show that G has a K coloring if and only if G star has a K flow. Right, then it works both ways. Okay, so let's first assume that we have a K flow, or for convenience, a ZK flow on G star. So part one is assume there's a ZK flow on G star. Find a K coloring of G. Okay. So from G, we get through our bijection that we have up there a map F on the oriented edges of G, simply let F assigned to an oriented edge little e of G as G of, take that little edge, take its dual under this map star, that is that little bijection there, that is an oriented edge of G star, and that has a G value. right? Notice here that E arrow star is something different from E star with an arrow either way. Right? Okay. So that's just a map for now, but we use it to define the coloring. And that's a nice trick. It goes as follows. Use F to color G as follows. We take a normal spanning tree. So, not just any spanning tree, but a normal spanning tree. And now we define the color of a vertex C of, what shall we call it, V? Yes, I think V. C of little v as the sum over all the edges E from the root R to V R, T, V, and this path oriented from R to V. Sum of all the F values of that. Right? That's an element of our group. We look at all the edges on the way from the root to our vertex V. Every oriented edge has a little F value defined in this way. And we sum them all up, and that's an element of our group which we use as a color. Okay, now let's show that this is a valid coloring. Right, we have to consider a neighbor U of V, and then prove that if it's a neighbor, it receives a different color. So here's an edge UV in G. R, if that exists, are U and V colored differently? Well, what is the color of U? It's the sum of the F values of these edges all the way up to U, but no further. The color of V is obtained from that by adding the F values of these two blue edges on top. Right. But U and V are now adjacent, and here we have an oriented cycle. This oriented cycle has F values summing to 0. So the difference between the colors of V and U, which is the sum of these, the F values of these blue edges here, is the same as the F value of this orange edge oriented down. Sorry, oriented up. Right, the sum of those two equals the sum of UV oriented up, because round this way they sum to 0. This is minus the difference of the two colors. So therefore, this equals the difference of the two colors, and the f of this is not 0. Right? Because f comes from our flow, and the flow is non-zero. Okay, so using normality, and where did we use normality? By saying that any neighbor of V is comparable with V, is below it or above it. If it had been above it, I could have done the same thing with U and V, swapping places. And the other direction is just as easy. So two given a K coloring, do I want to call it C? One minute. It's really only 1 minute. Okay. Okay, fine. Yeah. Okay, I'm sorry. So how do we define from this coloring an F, which then translates via this to a flow? We define, we do the converse of what we did a moment ago. So we define F of E of an oriented edge from V to W as C of W, the coloring, minus C of V. And we don't need colors in ZK here because these differences, since the colors are all positive, the differences are again going to be between strictly between minus K and K, right? So that then we need to show that this F here sums to 0 round every cycle, because then G will sum to 0 across every oriented bond, which is what we want to show. So if we take an oriented cycle, say this way round, okay, these vertices now have colors. So this, say, V, W, U, and so on. The F value of this edge is, from V to W, is this difference, right? So here, let me give it a color, not orange. So the F value of this edge is C of W minus C of V. The edge value, the value of this edge here, similarly is C of V minus C of U. And the value of this oriented edge from whatever to U is C of U minus C of this thing here. And you see that the C's all cancel out when we sum over all these edges. So the C of V, which is subtracted here, is added here. So each value under the coloring gets added and subtracted exactly once when we sum around these oriented edges where F is defined like this. So around either orientation, we get always a sum equal to 0. Therefore, across every oriented bond, we're going to sum to 0, and therefore we have a flow, a K flow on G star. Okay. Any questions? Sorry for the overtime. Thank you very much. And more on flows in the next lecture on Tuesday.